Modeling the electronic states across an entire crystal lattice presents a significant computational bottleneck. Solving the Schrödinger equation everywhere requires calculating a nearly infinite environment. This comparison contrasts the intensive full crystal problem on the left with the Kp perturbation shortcut on the right. This theory avoids infinite calculations by starting with known wave functions at a high-symmetry point, typically the gamma point where the wave vector k is 0, and using perturbation theory to map the states immediately nearby. This localized focus is sufficient because nearly all critical semiconductor physics, from photon emission and LEDs to high-speed carrier transport, happens at these specific conduction and valence band edges. Macroscopic device engineering does not require a model of the entire quantum universe. Precise perturbation at a single symmetry point provides the necessary data to predict device performance. The common engineering heuristic treats effective mass as a static property of the material, essentially assuming the electron simply acts as a particle that is heavier or lighter than it would be in a vacuum. While this scalar model works for simple applications, it fails when designing advanced high-mobility transistors or narrow-gap infrared sensors. We can resolve this misconception by looking at the top right quadrant of this matrix. Effective mass is a dynamical, emergent quantity. The electron appears to change its mass strictly because its primary energy band is actively mixing and coupling with remote energy bands. To engineer at the physical limits of modern semiconductors, we have to move past the idea of the heavy particle and understand the mechanics of interband interaction. The mathematical process begins by applying Bloch's theorem to the periodic potential of decrytal to isolate the periodic portion of the wave function, denoted as UNK. The resulting Hamiltonian includes a specific perturbation term. The equation deconstructs into three parts: the unperturbed base state, free electron kinetic energy, and the critical Kp coupling term. Physically, this term dictates that the conduction and valence bands must interact. We can observe the consequences of this interaction by using a foundational two-band model, considering just one conduction band and one valence band. The localized momentum perturbation acts as the engine of the system, tying these bands together and determining the transport properties of the final material. Diagonalizing the coupled Hamiltonian matrix forces the band energies to repel each other, a phenomenon called level repulsion. This quantum mixing forces the conduction band to bend upward and the valence band downward. The sharpness of this curve defines the effective mass. This summation formula proves the effective mass is not an intrinsic constant. It is the mathematical result of interband interactions, modifying the free electron mass. Consequently, the massive reduction in electron mass is driven specifically by strong conduction-valence coupling. An electron only behaves lightly because its energy band is actively mixing with others. The mass itself is a direct byproduct of this level repulsion. If interband mixing determines mass, we must ask why every nearby band in the crystal doesn't repel every other band simultaneously. Crystal symmetry acts as the absolute gatekeeper for potential mixing. To have a non-zero matrix element, state symmetries must be compatible with the momentum operator, like S-like conduction states mixing with P-like valence states. Incompatible symmetries result in zero mixing, keeping bands flat. Symmetry dictates which equations can couple, thereby predefining the shape of the transport channels before any external field is applied. For actual zinc-blende semiconductors, we move from the two-band model to the rigorous 8-band Kane architecture shown here, detailing the anatomy of the gamma point. This model incorporates a missing variable that is essential for accurate device physics: spin-orbit coupling. This interaction couples electron spin directly to its orbital motion, which significantly impacts the P-like valence states. The macroscopic consequence is the fracturing of the valence band degeneracy, separating it into distinct heavy hole, light hole, and split-off bands. This microscopic fracturing hard-codes the optical polarization roles and the specific hole masses that are exploited in modern spintronics. A standard parabolic model assumes a constant mass, but that assumption fails when an electron accelerates and moves away from the k=0 expansion point. As shown in this right-hand plot, increasing the wave vector k shifts the mixing ratios with remote bands, causing the energy curve to diverge from a simple parabola. This is non-parabolicity, the reality that the effective mass of the carrier actively increases with energy. This deviation defines the absolute performance limits for high-speed electronics and narrow-gap infrared detectors like mercury-cadmium telluride. We can unify these various behaviors through the Kane parameter P, which is the underlying momentum matrix element governing the system. This single parameter simultaneously dictates the optical transition strength, the transport effective mass, and the limits of non-parabolic deviation. Ultimately, KP theory is the translation layer proving that macroscopic semiconductor performance is engineered through microscopic quantum perturbations.